Okay, first I'd like to thank the organizing for letting me opportunity to present my results. I will talk about correlating transfer ionization and relativistic collision of highly charged ions and light atom. We would like to study electron correlation at high energies and in very strong fields. After this work, there was a number of studies of transfer ionization, but all the studies were devoted to light systems. The heavy system I know was the collision of lithium nucleus with helium atoms. So we need to extend theory of correlating transfer ionization to relativistic domain. And we'd like to investigate the role of Brett interaction in relativistic transfer ionization. We have found that transfer ionization is profoundly influenced by the Brett interaction, which is increasing changing the shape of the emission spectrum and considerably increases the emission. Here's a Feynman diagram presenting the one photonic change. This is a typical matrix element. Psi are the one electron Dirac Coulomb function. D is a photon propagator. Here it's written in Feynman gauge. This part presents the Coulomb interaction, and the Brett interaction can be divided as a difference between the total photon propagator and its Coulomb part. Normally, Brett interaction is defined in Coulomb gauge, but since gauge invariance take place, we can define it in this way. I'd like to give two examples of importance of the Brett interaction. Here are estimates for correction to the energy level, to the ground state of the two electron configuration. This is correction to Coulomb interaction and to the Brett interaction. And we can see that they differ by factor alpha z squared, what is 1/2 for uranium. Here's an example of d-electronic recombination with one electron uranium. Here is given a cross-section for this process. The black curve gives the full relativistic QED calculation. The red one is calculation with disregard of the Brett interaction. You can see that here the Brett interaction may increase the cross-section even 2 times in principle. So transfer ionization occurs in ion atom collision when heavy nucleus captures one of atomic electrons and one electron is emitted. It is convenient to distinguish correlated and uncorrelated mechanism transfer ionization. The correlated mechanism in the correlated transfer ionization and electron interaction play a crucial role, while in uncorrelated transfer ionization, the interelectron interaction is of minor importance and in principle can be emitted. Here is a scheme of correlated transfer ionization considered in the rest frame of the heavy nucleus. So the moving atom with at least 2 electrons, one electron is captured to bound state of the atom, and the energy exceed is taken by the second emitted electron. Transfer ionization in energetic and very asymmetric collisions, so very heavy nucleus and light atom, is characterized by change in electron momentum much larger than the typical orbiting electron momentum in the atom. Therefore, our consideration is based on the impulse approximation, where the incident electrons are considered as quasi-free. So in this approach, the transfer ionization is in essence a 3-body recombination. Amplitude of transfer ionization can be, in the first order of interelectron interaction, can be written in this form. Here J is a transition current of one of electrons, and the A is a potential electromagnetic field created by the other electron. In impulse approximation, the transition amplitude to momentum space can be written in this form. Psi gives the momentum distribution of atomic electrons, so-called Compton profile. This is the determinant of 2 free electrons wave functions giving the 2 incident electrons in the initial state. And here is the determinant of emitted electron and bound electron. during the final state. The cross-section can be expressed through the transition amplitude and momentum presentation in this form. This integration of momentum can be done analytically, and we come to this formula where C is a Compton profile factor. And I'd like to say some words about this amplitude U. This typical matrix element for this amplitude is given here. Here we can see three oscillating functions of electrons. It's two initial electrons, which free electron is the wave function oscillating with frequency equal to momentum, for initial momentum, and the function of the emitted electron, which is oscillating with momentum P3. And here is also photon propagator, which is also oscillating function. If the if the impact energy is large, then the energy of electron becomes close to momentum. And these oscillations start to compensate each other, what gives a considerable growth in cross-section. Physically, it means that the virtuality of the exchange photon increasing when the impact energy increasing. So the exchange photon becomes closer to the mass shell, what increases the effective range of inter-electron interaction, what gives growth to the cross-section. Here are combinatorial results. Here is considered process of collision of nucleus with Z60 with carbon. The velocity of collision is 70 atomic units. The process is considered in the rest frame of the atom. The left plot gives a calculation with disregard of the Brett interaction, and the right one presents the calculations with full inter-electron interaction taken into account. We can see the considerable growth of cross-section due to the relativistic effect and to the Brett interaction. Here you also can see two maxima at 0 angle at about 60 or 70 angles. And this notation, the ion beam is moving in a backward direction of z-axis. So all these electrons at 0 and 60 degree moving in the backward direction of the ion beam. The maximum at 0 angle is explained by so-called electron-electron Auger mechanism. The maximum at higher angle is appears only provided one accounts for the effect of a highly charged ion field taken into account on both incident electrons. So if we switch off the effect of Coulomb field of the heavy nucleus for at least one of the initial electrons, this maximum will disappear, while the maximum at 0 becomes just stronger. So the mechanism at this maxima are very different. Here's the same process, but considered in the rest frame of the ion. We see two maxima, one is 0 and another is about 25-30 degrees. Here's results for the velocity, collision velocity 70 atomic units and for various z. You can see that the transfer ionization is very influenced by the Brett interaction and the shape of the emission spectrum and the changing while we take into account the Brett interaction. And Brett interaction also increases the cross-section. Here results for velocity 90. And here for 110, we see here that the influence of the Brett interaction is particularly strong. Here are results for total cross-section. In the first column is given velocity of collision. The next two columns shows the collision system and the charge of the nucleus. And this column given results calculated with disregard of the Brett interaction, so only Coulomb interaction is taken into account. And here the Brett interaction is taken into account. And here is the ratio of these results. And we see that for large impact energies, taken into account Brett interaction may increase cross-section even in order of magnitude. And so I come to conclusions. The theory of correlated transfer ionization in symmetric ion-atom collisions is extended to relativistic domain. Then for considered collision systems, there are two maxima centered at 0 and 25-30 degrees. The first maxima is due to so-called electron Auger mechanism. The maximum is larger. Angles is provided, appears only provided one accounts for the effect of Coulomb interaction with nucleus of highly charged ion and incident electrons. And the process of transfer ionization profoundly influenced by the Breit interaction. So, thank you for your attention.